So I start with something that happened 26 centuries ago. And you know, there was this philosopher and probably first mathematician, Thales. Of course, this portrait is, it's all imaginary. The portrait was made probably 500 years after his death, but no problem. So, as you remember, he was known for the theorem. There's another theorem, at least two theorems of Aristotle, but this one is the most widely known, and he was able, due to this theorem, to evaluate the height of the pyramid, Great Pyramid in Egypt, that is still there. And it's also amazing that at the time, so 26 centuries ago, the pyramid was so old, it was almost 1,000 years old already. So the information about its height was already forgotten. So he was able to evaluate the height of the pyramid by comparing the height of the pyramid with the height of a stick, vertical stick, and the shadows, two shadows. So this is extremely simple, but this is a physical experiment. It's not only mathematics, it's a physical experiment. And what is interesting that in this experiment already, there are some questions and some problems that we are struggling with even today. Because the interdependence of what is geometry and what is matter and what is all this. So the relationship of proportionality is, of course, but it proves something because he was using three different types of definition of what is straight line and what is right angle. So these three definitions went from three different domains of physics. One, straight line and right angle came from gravitation. He was using gravitation, as people used the gravitation, to know what is vertical, what is horizontal. So these first assumptions are that the stick and the pyramid were parallel horizontal, vertical, and the ground is horizontal, and there is the same right angle here and there. Another thing is the straight line, that the stick was straight. This comes not from gravitation. This definition of a straight line comes from, by now we know, it comes from, this is gravitation, you see? This is how we know what is horizontal, what is parallel, and what is the right angle. Okay, this is even now. But there is something different, that the stick is straight line. This comes from, as we know now, this is quantum physics. This is because there is stability of matter. And for example, we can grow crystals in where there is no gravitation. We can grow crystals and know what are the angles and what are the straight lines from this crystalline growth. So the matter itself also defines straight lines, but this is material geometry. It has nothing to do with gravitation. These angles, it is completely independent. This is just for illustration, how we know what is straight, what is right angle from matter. And this, of course, this comes, as we know now, from quantum physics, from the stability of matter.
And there are some experience of growing crystals in the cosmic.
Yes, of course. Yeah. And they grow perfectly well. They do not need gravitation. Of course. It has nothing to do. Gravitation is so weak at this scale. Nothing to do. So you have material straight lines and the gravitational straight lines, which are, of course, the equipotential surfaces and the. But there is, of course, this is not the end. There's another straight line, which has nothing to do with this. This is the light ray. This straight line comes from propagation of fields, and it is not matter. It is not the material thing. It is just light propagation. So what he proved is that there is some interdependence, that all three definitions of straight lines and angles, somehow come together. So there is some interdependence. And whenever we have, like in thermodynamics, if you have a dependence between P, V, and T, temperature, pressure, so we say, come on, maybe there are two which are independent and another which is dependent, maybe derived from them. Because you have, for example, here it is quite easy to understand which one of these three domains of physics could be postponed, and you still have the theorem you can prove. You have light rays and sticks and no gravitation. Because even with sticks, with crystals, you can define the right angles, you can define the straight lines, and all you need is the light ray, and that's it. You could do without gravitation, of course. So now, I can skip it because I said already. Now let's go to, so this is, I said it already, so I can skip, and now we go to some generalization. So what this Thales experiment was telling us is that there is an interdependence of these three geometries which come from three different realms of physics. One is space and time, because here we play about this straight lines and we define space and time, we define geometry with these straight lines and angles. Another are material bodies, and finally there are forces. And I deliberately, the forces and material bodies should be separated. Now, in modern language, this separation, if you dig inside, it is between fermions and bosons. The bosons are intermediate forces, and fermions are, because of Pauli's exclusion principle, they are at the root of stability of matter. This was known since Pauli and Ehrenfest and Dyson did very beautiful articles on stability of matter, that all this is based on Pauli's exclusion principle, on the fact that the fermions cannot occupy the same state, because if there were only bosons, everything will go to one single state, and there will be no matter, nothing. Everything will be. So that is why I make distinction between what I call matter and forces. So this is also something that is extremely well known, but if you look at this, I divided it, I wrote it in this a little bit unusual way in order to divide, and now there is also a digression that for mathematicians, whatever you write, no matter how you write, you can write it all on one side and say it's equal to 0. It's just the dependence which is important. So whatever depends on which, it's just symmetric. But for a physicist, you can distinguish between cause and effect. Something that is the source of and something that results. So here, for example, it's easy to see, what is, this belongs to space-time. The acceleration we measure, in order to measure acceleration, we have to measure space and time and divide one and the velocities. So this is space-time. These are what I call forces. This is the most mysterious thing, where it comes from. And these are these material bodies. Without these material bodies, you will never know whether there are forces, and you will never see acceleration. To see the acceleration, you have to have something, and this something, to produce acceleration, you must have. So this is, of course, all this is on the side of cause. So the real cause is the presence of forces, whatever it means. Of course, these are these intermediate fields. For example, these forces, whatever we do here, whatever forces we use, when we go deeper and deeper, it is always electromagnetic forces. There is nothing else. accessible to us, because the strong interactions are so hidden, are so inaccessible to us, that so whatever forces we are using, even here on the table, it is all electromagnetic forces just screened by quantum effects. They are not long range with the van der Waals forces, but they come from electric charges and screening that comes from quantum theory. Okay, so now, yeah, this has already been said. Yeah, and now how can we translate it into more modern language? What can we do with this? So, as I said, let us see these three realms of physics: space-time. I made a three-dimensional, and now first exercise in combinatorics. Yeah, how to take 2 out of 3. So to take 2 out of 3, there are only 3 ways, and there are 3 different types of theories.
You are talking about 3 different possibilities, but it seems to me that principle of minimal action lies behind all of them. Fermat principle, no? Because you minimize the action and you get
action of what?
I don't know. For instance, for the light, you minimize time of propagation for growing crystals, wolf shape or something like that.
Yeah.
Everything you have something you write like in Hamiltonian, so you minimize the action, you get the forces.
This is mathematical trick. This is mathematical description. It's not physics.
Okay.
Okay, we can discuss. No, the fact that you can use something, some mathematical language to describe many different things, I agree. But it does not mean forcefully that these things are related.
Okay.
For example, you take Bessel functions. Bessel functions were used from, Bessel was an astronomer, and he wanted just to know how to describe the elliptic orbits and how to make explicit Kepler's equation, which is implicit. And there is absolutely no hint that the same functions will be used in cylindrical, for example, cylindric conductors with electric field. There's nothing that will tell you that from astronomy and from Bessel functions that are used here, you come there. And still there are the same Bessel functions and the same equation. How do you explain this? It does not mean that the same principle is in the cylindrical conductor and in elliptic orbits around the sun. They are from it's different physics, but the mathematics is exactly the same. Okay, so now let us see what can we do, and there are of course 3 possibilities if the idea is that one of these things depends on 2 others. So for example, there are 3 different we'll have 3 different types of theories. One is, for example, there is only space-time and matter. There are no fields, no need for fields, no need for intermediate. And of course, you recognize what it is. This is Newtonian physics. Newtonian gravity, Newtonian physics does not know any propagating fields. It is action at a distance. Whatever you do here is immediately reflected everywhere and the space-time is something that exists absolutely independently of matter. Space-time geometry is there, and matter is playing things without any intermediate fields. There's no notion of fields. Now, so this is without fields, matter and space-time. Now another combination is space-time and fields, no matter. This is, of course, this was advocated by Kelvin, and this is roughly, this is the red line that comes, the thread that comes until now to string theory. You don't need matter. There's no such thing. It's just vibrations. You have only space-time and fields. And the string theory tells you even fields, everything is just strings. Whatever, there are just excitations. The space-time, whatever, everything is just excitation of strings. But for Einstein or for Maxwell, there was no problem. There was only fields, and the dream was to explain matter. Kelvin was also, Kelvin, for example, had a theory, the first theory of strings. Kelvin said that atoms, the fact that they have these vibrations which are different from one atom, it is because atoms are nothing but strings, but the singularities in the ether, and the singularities can have different topologies, like different knots, and every topology has its own vibrational modes, and that's it. So the atoms, there's no matter. There's just like in helium, you have this. But for them, there was no problem. The space-time, they were in this sense, they were Aristotelians. There is no such thing as empty space-time. It is filled with something, with ether, and of course the distance, whatever. It's like for fishes, for example, a fish distance from one fish to another in an aquarium, it can be defined as just the quantity of water that is between us. So if you have ether, you don't need geometry. You have it. It's just as material as the rest. So you have space-time filled with ether, which was called by Aristotle quintessence, because there are four different substances in elements, but in the sky, in the space, there was the fifth element, the quintessence. Okay. So, and finally, there's a third possibility. There's matter and fields. Matter and fields. And what we call geometry, what we interpret as geometry, comes from is inherited from the groups that are acting inside. For example, this is why people say, usually we say that SL2C is a double covering of the Lorentz group. So by some miracle, you see, we have Lorentz group here acting macroscopically, and somehow when it goes inside, down there it splits into two things. It's more natural, in my opinion, to think that there are these two distinguished things that operate in Hilbert spaces, and what we see is the average between the two, and we see only the Lorentz group, which is after this double covering, it's the other way around. The Lorentz group is just the average of what is real, and the real is this double covering. This is SL2C, which has two distinct representations in Hilbert space of fermions. Okay, so let's go now. So see, under this angle, you don't need space. You don't need space-time. It is just concomitant of what is going on in Hilbert spaces, in states, in quantum states. After averaging, we get something, we see something as space or time. And to tell the truth also, and again, what is really fundamental, even in these Hilbert spaces, are the discrete symmetries. These are the most fundamental ones. For example, Pauli's principle or conservation laws, you have this discrete charges, discrete baryonic charges. So this is the basis, and what we perceive as continuum comes only from the fact that there is another principle in quantum mechanics, which is superposition principle. If you have any two states, you can make a superposition, it is also a state. So after many, many superpositions, we get something that looks like continuum. But the basic things are discrete. Yeah, so again, what I would like to say, we usually also because we operate, we live in what we call space-time, what we perceive as space-time, of course. So in any physics manual, K and omega, for example, energy and momentum, they are called dual space. But if you look what is really going on, the Lorentz transformations are operating on conserved quantities, which are energy and momentum, and this x and t are dual. We live in dual space. The real space is energy and momentum. This is the physical object on which this SL2C or Lorentz group acts, as it acts on photons, for example, on propagating fields. And it can be the Lorentz symmetry could have been in principle just discovered just by observing the transformation, how omega and k, how frequency and wave vector, how they transform from one Galilean observed to another. This is what is really going on. And then from this, we infer that because we can write the invariant, this is an invariant. So if these two guys undergo Lorentz transformation, so as invariant, the other two also have to undergo the contravariant one. So this is why we live with Lorentz transformations. But what is really going on, the Lorentz transformations concern physical quantities which are conserved, which are real. You cannot measure x or t. Absolutely. These are not conserved quantities. They are not physical. So again, now let me I will accelerate. So now, as we know now, the ultimate components of matter are, for the fermionic matters, are quarks and leptons. And quarks are as small, roughly, as electrons. The quarks are for a nucleus what nucleus is for an atom. It's about 1,000 times smaller. And this is also experimentally known because there is deep inelastic scattering, and it enters into, and then the diffusion is roughly like what Rutherford made with an atom. You see that there are almost point-like structures inside. So we don't know any other constituents. So now what we want to derive, how to derive, well, not Lorentz symmetry, but SL2C group, how to derive it from very basic properties, discrete properties of fermions and of quarks. Okay, so let us see. This is, of course, again, to show that there are three. I deliberately say three because gravitation is really something else. It is different, apparently. It has no role, as for now, in microscopic world. We don't see any influence of gravity. Of course, maybe this quantum gravity is always a dream, and maybe it played a role at the very beginning of Big Bang, but actually, in the universe we live in, it has absolutely no role in microscopic world. It cannot be seen. And these are again, this is the composition. You have 6 different quarks, but I will start only with this, which form protons and neutrons. These are exotic quarks. These are leptons. This is also interesting symmetry, that there's exactly the same number of leptons as the number of quarks, and the same number of families. And these are propagating, the intermediary fields, which are bosons. And I didn't write Higgs, because Higgs permeates everything, and probably it is one of the next avatars of ether, in a sense. Okay, so this is, again, there's also color, which is like spin, but it has three different possibilities, exclusive. You cannot have two colors in one and on the same state, always different colors, and always three. So this is just to amuse the audience. And now, yeah, so now I'm starting to write some formulas. You see, again, this is what you find usually in textbooks, that you have the representation that, for example, if you have a wave function belonging to some Hilbert space, L2, a wave function that describes some matter field, some electrons, say, or quarks, whatsoever. Then, in order to make it compatible with Lorentz, with geometry of space-time, we say that there is a representation if the same function of transformed x is the same as the old function, but transformed by another representation, which is here, for example, spinorial. It's for Dirac field, it's like this. This is spinorial representation. Lambda is some Lorentz transformation. So Lorentz transformation acts on space-time, and miraculously, what is going here, for a single electron in his Hilbert space, there is something that is, but we can adopt another point of view, just the opposite, which will be like this. Instead of writing this, what is also important that you see that as usually very, very deep physical equations, they are deep like Einstein's equations, that they make an equality, they set an equality between things that belong to completely different realms. Here you have space-time, sorry, and here you have Hilbert space. So something that happens in Hilbert space and something that happens in macroscopically, somehow, like in the Thales experiment, they come together and they are somehow compatible. But if we adopt this opposite point of view, one should write differently. Not like this, but exactly the other way around. Yeah, like this, for example. That what is going on, for example, take Dirac current, which is an observable thing. It is a 4-vector which transforms under a vectorial Lorentz. But why it transforms so? It transforms so because this vectorial current is something that is created by a fermion, by Dirac field. And it is a bilinear. It's a bilinear combination. This is why we will not see any difference between two different representations of SL2C, because they eat each other. So what is left is the average. So in principle, it should be written like this. There is something that happens in the Hilbert space that changes the state. Then the current it creates has to undergo, the transformation. So it should be like this, that this macroscopic transformation depends on SL2C that acts in the Hilbert space. Mathematically, it's the same. Probably there will be some very clever people who say that there is a functor or something that transforms one way of seeing it into another. I don't know if it's so, but let us take this point of view, that what is really determining the group and the geometry is happening in Hilbert space of states. And the averages, what we get from it, reflect these transformations that are there. Okay, so let us see. Even the x mu, which we measure, are measured with some devices, so they also undergo, we define space and time because we can have these devices or electrons or whatever with which we the matter. So if matter is transformed, then x mu is transformed too. Good. So now let us try to derive where this SL2C comes from. If we forget the macroscopical world, what in the microscopic world, what decides that there must be this SL2C symmetry? Then this, again, I think I have to skip. How much time do I have?
You have 10 minutes for, and then 5 minutes.
Yeah, okay. So,
10 minutes.
yeah. This is again what is behind the forces. Behind the forces, you have always some current. So this is how you produce the influence, and this propagates with the speed of light. Okay, this is, I skip because this is standard thing, how you, and let's go from Dirac equations. Yeah, now you see that this SL2C acts on two Pauli spinors which compose the Dirac spinor, and this is how it works. And again, once we produce currents, the currents undergo the representation of the same SL2C, but as a Lorentz transformation. And the currents being conserved, you see how it works, and then you see that there must be mass or no mass, but there is a Dirac equation. Dirac equation can be derived just from the conservation. Okay. Now, I skip this Dirac equation. Again, we have all these transformations as they should be. So now let me see. This is again how the matrices, Dirac matrices, transform. They have also to transform under. You see, this is because they are not simple spinors, because they are like quadratic combination of spinors. So you have S minus 1 S, and here you have. This is how the Dirac matrices transform. Okay. Now, so let us go to Pauli's exclusion principle. Yeah. So what Pauli says that usually they say that this is because the functions that describe the tensor product of two states have to be antisymmetric. Again, this is what is usually said, but the trick is that it comes from Pauli exclusion principle that says only that that the state cannot be occupied by two things. So this says only that what you have to have that this is the most important thing. Instead of saying that this is the result, you say you start from this. You start from this that phi x must be 0. And then you use the superposition principle. So if you have two different states, you call it z, and then you say that fzz should be 0. Because it has to apply to any combination of states. If so, you just develop it, and you see, again, this is 0 because we suppose that no. This is also 0, and then what is left, beta, alpha, alpha, beta, they are just simple numbers, and then you get the antisymmetry. Okay? So antisymmetry is coming from Pauli's exclusion principle and superposition. Okay, so that's what we see. After second quantization, you get anti-commutation, and then so what it tells you is that in Hilbert space of states of an electron, say of a fermion, take an electron. Whenever you have two electrons which have exactly the same quantum numbers, they have only two possibilities. There is something that is called half-integer spin, and they can be only two possibilities, and these two possibilities are antisymmetric. Either first one is up, the second down, or so, and these states are antisymmetric because of Pauli's principle. So if so, and now we say, okay, but there is also superposition principle. If it is valid in some chosen basis, it should be valid in other bases of Hilbert space, the same. So if so, any matrix transforming these two sectors of Hilbert space should act on this invariant. This form should be invariant. So if it is invariant, look, this is what you get. These are the equation, constitutive equations. And of course, what you get is that this 2 by 2 complex matrix, 2 by 2 complex matrix has to have the determinant 1. This is SL2C. This is how SL2C comes naturally from Pauli's exclusion principle. So now, and from this, of course, you get up and you get Lorentz group and so on. Now, there are quarks. This is the Lorentz, this is the standard representation of this algebra, SL2C, which is the same as the Lorentz algebra. The Lie algebras are the same. Okay, and now I wanted to to tell you what is there is something else that appeared in this first model, that there are two types of quarks, up and down, but these are not like fermions. They are Pauli fermions, but there is something else. There is some different statistics that you can have two of them, but not three. You can UUD or UDD, but not UUU or DDD. So what kind of statistic? It looks like Pauli's principle, but a little bit different. So it is, in fact, it is not Z2 group, but Z3 group that is acting. And of course, there is SU2 group, but this is just the symmetry group of the whole thing. But now, how come that? There is also the Gelman-Okubo formula that gives relationship between baryonic number and electric charge. And then if you apply, of course, there are mesons too, which have baryonic number 0. And what is interesting that if you apply this Okubo-Gelman formula to quarks, then you see, because you have 3 quarks for 1 nucleon, the quarks must have this y equal to 1/3, because y of a proton or neutron is 1. It's a baryonic number 1. So any quark must have 1/3. But what is also interesting, that also the charges become, U becomes 2/3 plus 2/3, and D becomes minus 1/3 electric charge. Okay, so now what we want to see, that we can have some new statistics that tells you that you cannot have 3 identical things, but you can have 2. So you see these generators of the new algebra of quarks, this can be not 0, not like for electrons, not like ordinary fermions, but the third power should be 0. So again, I use the same idea, no 3 possible states, and principle of superposition. So let us start from this. No, this must be 0. Then you make a superposition of 3. Now, of course, 3, you'll get how much? How many? 3, 3, 3, 27, if you take the third power. So you get, sorry for complication. Well, but it's simple. It is, you get 27. Out of this 27, this one is 0. This one is 0, and this one. There are 3 that are 0 because they are diagonal ones. And we suppose that there are no 3 identical. So what is left? 24. Out of this 24, you have 3 different groups by 6, and 6 different groups by 3, and 1 group by 6. All in all, 24. How to solve it? In Pauli's principle, in ordinary, there was -1, which was the generator of Z2 group. Here you must have a generator of Z3 group. Z3 group is the root of unity, but third root. I call it, let's call it J. Okay, like this. J cube is 1. And that's it. So this is the symmetry. instead of having phi xy equals minus phi yx, you have psi phi xyz is the same as j yzx and j squared, and then you turn again and you are back. Okay. Now, again, let us make an algebra like Grassmann algebra that used in Pauli's principle. The same thing. And of course, here you have choice of two things, because you have j, it's 1, but you could have used j squared this way or this way. So you have conjugate algebra 2, like this. That's fine. And then we have to complete the commutation relation between thetas and conjugate thetas. And this is minus j. Again, if you turn it around, it's okay. So now there's something that is quite nice surprise, that you have no 4 powers. You can have 3 quarks, but no 4. No, impossible. It is nilpotent algebra, and it ends up with power 3. And whenever you put 4 of them, whatever the dimension, you see how it works. Of course, it is supposed to be associative. If it is associative, you just turn around, A, B, C, you put C here, no, A here, and then you get factor J. Then I will put C behind, I get another factor J. Then I have to put B behind, I get J3. J3 is 1, but I am still not back. This is because, of course, you know that 4 and 3 are relative primes. That is why you cannot be back with 4. And then you got once again D back. Now you are back. But unfortunately, what we got here is not 1 J. So the only solution is that it has to vanish. This is why we don't have 4 quarks or more, only 3. And again, the same thing with, but also what is nice that if you take the constitutive relations with theta bar equals minus j theta bar theta, and you get, of course, if you have 2 such combinations, they are nilpotent because, but you can have 3 thetas and 3 theta bars, they are different. And then you get, and you see they anti-commute. Fantastic. So it works like with 3 quarks you make a fermion. Very good. Now this is again, I replaced this theta, but there are only 2, u and d. So we have this algebra of these states, these operators that create d and u. And now the problem is there SL2C? How SL2C is present here? Because it was quite natural in Pauli exclusion principle, in electrons, in fermions, usual fermions. But is it possible to derive it from here? Yes, it is. Yeah. Let us skip and let us see. So we have, if these things are Pauli fermions, they have also an upper index 1 or 2. 2 states, 2 spin states, ordinary spin states. The isospin is u and d, and the ordinary spin is 1 and 2. And as you can see, if you have 2 u's, because they are spinors, they cannot have 1, 1. That's impossible, Pauli principle. But d can be 1 or 2. So you have this thing, or d1, d2, okay? So you have 4 different components, and 4 different components for, but this is what is necessary to create a Dirac spinor. That is what we need, Dirac spinors and anti-spinor. Very good. And now, so again, these are the relationships because we impose this algebra, Z3 symmetric algebra, skew symmetric algebra. This, and now I say, okay, we can make an average. It is exactly the same, you see, because whenever you do it, it's 1/3 of this. So we can, something that can be, it looks like a 3 form that has, and 3 form that is conjugate, And let me see, like exactly like this, I could write it with two forms that is skew-symmetric. I can introduce such a form. Look, I call it rho. So it has these properties of symmetry. It is exactly the analog of epsilon alpha beta for usual fermions. But for these quarks, it should be like this. And what is important, these are the components. And of course, there are two different, I put 1 and 2, because 1 is 1, 2, 1, 2, 1, 1 on 1, 1, 2, because I turned the lower indices. And 2 here, because this combination is different. You have this, again, combinatorics. There are only two combinations. You cannot have 1, 1, 1 or 2, 2, 2, but you have a 1, 2, 1 or 2, 1, 2 for spins. So these are the only possible combinations, and of course the conjugate ones. Again, so this is the, so now let us see what, this is again how we can write with averaging with this rho. And then I say, okay, if so, it should work. This form, these two forms, they should be invariant under any linear transformation. I need transformations that they keep this form invariant, like was with epsilon. So this is, but here it is not only invariant, it is covariant. Remember that these combinations of three different quarks should result in a Dirac fermion. But we know that Dirac fermions, well, here it is just Pauli fermion because we lack the other part. But they transform with SL2C, right? So if so, these three acting here should be the same. You see, it's exactly what we did with Lorentz transformations. There's in one realm and in other, from quarks to fermions. So we have to have these transformations. So now this I know, this is SL2C, determinant 1. So what are these? Okay, I'm just one by one, I'm looking what it gives, and look what it gives, because of this transformation, you have j squared and j plus j is minus 1. So two of these come together, and you see, okay, as this component, this diagonal component, is like the same like SL2C, but it is multiplied by the determinant. Fantastic. The same with other three. And finally, the result is that you got also the matrices, 2 by 2 matrices, complex matrices, which but the determinant can be not only 1, because the cube of their determinant is the determinant of SL2C. So you have three different realizations with determinant equal to j squared, or 1. This is, again, Z3 covering, one can say. So you see that these quarks, they also have their own SL2C, which once put together by 3 gives the SL2C that is known in fermions. And once again, from these fermions, if you construct currents, then we see the ordinary Lorentz transformation. So this is roughly the end. Just recent papers on this, because I didn't speak about colors. So thank you for your patience, and that's it.
Thank you very much. Raise some questions. I'm not familiar, so probably you know, is it possible to derive path integral for these kind of Z3 symmetry and
I hope so. I hope so. That would be interesting. Of course, of course. Yeah, yeah. Because it's different statistics, but it is not that difficult. Instead of binary, you have ternary, and you have the phase that is E2. I think this is possible, but probably it has to be.
I have some feeling, maybe it's wrong, that it might relate to fractional statistics. And no.
Maybe. No, this maybe. You can call it fractional statistic because it is.
In the normal sense that you have a term and.
Yeah, but here you have always square roots of 1.
Yeah.
Or third root of 1. Or sixth root of 1 if you combine the two. This is about roots of 1. But no, I think that it should be possible, of course. No, there are many things to play with. That's for sure.
Yeah.
Yes. When you said, and this is why we have 3 quarks, isn't it the case that you should say, oh, this model is forcing the existence of 3 quarks? Because in fact, for the physical world, you could have some other models, perhaps, which could be compatible with other...
No. Sorry, maybe I was misunderstood. I mean, stable bound states of quarks can be only made with 3. Stable bound states. It is not that there exist 3 different quarks. No. This is a completely different problem. With these quarks, and I just touched no exotic quark, just U and D. And with U and D, you can produce neutron and proton, and that's it. All others need charm or strangeness. So this is a completely different story, which is also dealt with in other papers. But here, when I say 3, that you can have 3 and not 4, it is just to say that in stable configuration, if you want to create something that looks like a fermion, like Dirac fermion, or Pauli, 2 Pauli fermions, you can do it only with 3 quarks and not 4. With this statistic, it gives you immediately the reason, because it's just nilpotent. It should be nilpotent, because if it were not, you'll get other states too, but they are not observed. There are, of course, some observations. They are called pentaquarks or tetraquarks, but these are resonances. They of course, they last about 10 to minus 8 seconds, which for this kind of forces is quite long. But they are only resonances. They are not stable things. By the way, even neutron is not stable because of weak interactions. Neutron lasts about, free neutron can last about 10 to 11 minutes. That's all. And that it just ejects an electron, it becomes a proton. But proton, that is something absolutely amazing. Whenever we try to determine the lifetime of a proton, by now we know that it is more than 10 to 33 years. So this is, again, imagine someone that will sell you a car and tells you, I give guarantee for 1 billion years. You say, what for? This is what we are doing, because 10 to 33 compared to 10 to 15 is just almost 20. What for? This is also something that is amazing. But it's like this. Proton is indestructible.
Okay, so some other questions, please. Okay.
I have a very strange question. So here you looked at 2 and 3, and if you look at the combinatories, can you imagine other? Yes, like other, like, or it's
no, 4, no way, because it's not a prime number.
Yeah.
5, Galois theory tells you that you will not solve it anyway. I think that it stops at 3.
Okay, so that's a strong sign then. Yes.
Yeah.
Okay, 3 is.
3 is the last one.
Thanks.
Yeah. 3 is the last one. By the way, 3 is the last one. For example, S3. If you take the full permutation, S3 is the last permutation group, symmetry group, that has a faithful representation in complex space, in complex numbers, in C. Mm-hmm. If you go farther, it's impossible. You have there's not enough space. So 3 is also for this reason you can play with 3 in Hilbert space, and you'll always see everything, but not with 5.
Yeah. Okay, so thank you very much.